All right, welcome back. Sorry, it seemed like it got cut off. I wasn't watching the clock. We're back in chapter 7, still talking about light. You may have noticed I'm over in the corner over here now. That way I'm not hiding any of the graphics. Picking back up, still talking about reflection. So we were talking about why you've got light. Coming off of all these different points of the tree, why you get the undersides of trees lit up because of this property of diffuse reflection, because the surfaces aren't smooth. So you guys have actually seen diffuse reflection in action other than just seeing objects lit up around you. Something that you're very familiar with, I'm sure, is with road surfaces. So when you're driving down the road, the way that the road looks to you and your visibility on the road is actually determined by the amount of diffuse reflection. So if you are driving down the road and you've got that rough road surface in front of you, that diffuse reflection coming off of the road, bouncing the light from your headlights around, is actually what's going to allow you to see what's ahead of you on the road at night. So when your headlights hit that road, the light scatters in all different kinds of directions and spreads the light out, not just right in front of your car, but out in front of you, up onto the trees and around you, and out to the sides of your car. Now, you may have experienced this before if you've driven on the road at night after it rains, that your visibility actually shrinks quite a bit. And this is because a wet road surface is no longer rough but smooth. It works more like a mirror. And so it fills in all of those little cracks and bumps so that it's just kind of a flat surface. And so instead of the light bouncing and scattering and spreading out, the light more just comes right in and goes down and bounces up and out. And so therefore, instead of getting that diffuse reflection, the light is mostly getting bounced up and away from the road. And that's why your visibility shrinks during night times when the road is actually wet. So you can actually give this a try as far as diffuse reflection goes. If you grab yourself a piece of paper towel or a napkin or something like that, take that piece of paper towel, rip it into two pieces, and get one piece just a little bit wet. And then hold them next to each other. You can hold them on your hands or lay them on a table, and you should be able to see which one is going to be appearing darker to you, the dry one or the wet one. You can do that with a paper towel, or even if you just put a drop of water on a surface, the same thing will happen. So what is going on? Because the wet surface is going to look darker. What happens is when you have a wet surface, the light is actually going to go into that wet region where the water is at, and it's going to bounce around inside of the water droplet. And every time the water bounces inside of the water, it's actually going to absorb energy. So it's going to turn it from that light energy that's going to get reflected back into one of those other forms like infrared energy. And so since it's absorbing that energy, there's less of it to be actually reflected back to your eye from that wet surface. And so that's why wet objects look darker to us, because there's literally not as much light to be bounced back off of the object for us to see. All right, so we've talked now about reflection with rough surfaces. Now, reflection with smooth surfaces actually have very specific rules. So when we have a smooth surface like a mirror, so a flat reflective surface, what we can look at is this guy down here, this diagram. We've got what we call an incident ray. Again, that's the incoming ray. We saw before incident light. Incident is incoming. So that's going to be our light that's coming into the surface. And then obviously makes sense that the reflected ray is going to be the outgoing light from the surface. So the incident ray comes in, hits the smooth surface, and the reflected ray is going to go out. Now, the thing is that with a smooth surface, every time this happens, it's going to happen the same way. And that's why we have this normal line on one of these diagrams. And this is a reference line that runs perpendicular. You can see that in this diagram. It runs at a 90-degree angle to the surface where the point of where that incident ray struck. So where the incident ray comes in, we're going to put that as the point where the light hit, and then the normal ray is going to run 90 degrees straight up from there. So why is that important? Well, the thing is that we can measure the angle between the incident ray and the normal and the reflected ray, and with smooth surfaces and reflection, those measurements, those angles are always going to be the same. So if this angle between the incident ray and the normal ray is 20 degrees, the angle between the normal ray and the reflected ray is also going to be 20 degrees because that's how the reflection is always going to work with a smooth surface. It's always going to be equal going in and going out. It never is going to change if the surface is completely smooth. The only time that would change is if it is a rough surface, and then you get that diffuse reflection that we've been talking about. So there's another diagram with all of that kind of written in. So again, we've got our incident ray, our normal, our reflected ray. And so there's that. What I've been talking about is specifically, the name of it is the law of reflection. I know, surprise, another law. And so the angle of incidence, or the angle, that's the name for this angle that I was just talking about, the angle between the incident ray and normal, is going to be equal to the angle of reflection, the angle between that normal and the reflected ray. So that those two angles are always going to equal each other. So if this incident ray is coming in at a less steep angle, then the reflected ray is going to leave at that less steep angle. All right, so we're going to switch gears a little bit, and we're going to talk about specifically image formation. This is related to things like mirrors. So the first thing we need to talk about is what a real image is, because there's a difference between a real image and then the images that we see in something like a mirror. So a real image is located where the light is at. So what do I mean by this? So a real image would be something like, for example, the image on your computer screen. The light is being generated at your computer screen, and that's creating your image. For example, if we were in the classroom, the projector is projecting the light onto the screen, and that's where the image is at. It's literally where the light is at making the image. Or at the movie theater, those movie images are, again, like we would be in the classroom. The movie images are being projected from the projector at the back of the room up to the screen at the front of the room. This is different than what we see in a mirror. Mirrors are what we call virtual images because what you have is an image where there is no light. The virtual image is the same size as the original object, but it's formed behind the mirror's surface. So if you take a look over here at the picture, we've got this cube. This is the original object, and you can see that the cube in the mirror is the same size, and it is also located at the position roughly at the same point behind the mirror as this guy is in front of the mirror. So why is that? And that is because, as it's saying here, it's at that position where the extended reflected rays appear to converge. So if you take a look, the light is bouncing off of the object to the mirror, And those light rays then reflect off the mirror to your eyes. If we trace those back, your eyes are seeing the reflected rays, but because it's looking at that flat mirror surface, if we trace the rays back, straight back, that's why that image looks like it's behind the mirror, because our brains are putting that object straight back in the same line as those light rays appear to be coming from, even though they're actually just getting bounced off of that mirror originally coming from the object that we're looking at. And you probably are a little familiar with this. You may not have actually ever noticed it, but an object appears as far behind the mirror as the object is in front of the mirror. So if you can't actually, reach the object behind the mirror, but if you were to set up a mirror and place an object in front of the mirror and then try to set something behind the mirror while you were looking at the one in front, then you'd actually place the other, pin or whatever it is roughly at the same location behind the mirror, because that's what you're actually, your brain is interpreting as where the location of that object is in the mirror. And that's the thing, is that this virtual image, that object, that cube or whatever it is you're seeing in the mirror, isn't actually there. And we know that, but it looks like it is to us. And this is because of our eyes and our brain putting that information together from the reflection of the rays and that flat surface to put that image into that surface for us. But the problem with it being reflected rays is that, as you're familiar with, the image gets flipped. And so this is why things look like they're backwards in a mirror, because the rays get flipped around when that happens. I don't know how many of you may have been to a fun house, but something you often will find in a fun house are curved mirrors. And so you will find these guys where they've put bends into them. There are two types of curved mirrors. These do work in the same way as a flat mirror, but that curve does change some properties of the mirror. And so the first type is a convex mirror. Convex mirrors are what you're seeing over here in diagram A, where the curve goes out, so the mirror is curving towards you. And you can see the incident rays are coming in, and then when they bounce back towards your eyes, they are going to change what the image looks like. Because what has happened is those rays are being pulled closer together because of that convex curve. And so in a convex mirror, the image is smaller and closer to the mirror for that virtual image than the actual object is. And so the nice thing about convex mirrors is they do increase the field of view because they shrink objects. And so you don't need as big of a mirror in order to see a larger area. So where do you commonly see convex mirrors? These show up on your car. So if you look over here, if any of you have one of these little extra curved mirrors like this on your car, or if you've seen them on trucks, that's what those little mirrors are for, is to give an extra view around that vehicle. Some places you'll see them in driveways or parking lots so that you can see around corners or blind curves, things like that. So that way you've got that bigger field of view so that you're not going to be running into cars and things like that. The other one is a concave mirror. This is B, it curves inwards. It's the opposite. So it ends up creating an enlarged virtual image. We often see these in shaving and makeup mirrors so that we get a larger image of what we're looking at. All right, we're going to wrap this section up and we'll get to the next section in our